Hello, today we want to discuss about another type of renewable energy that delivers constant power output. We will talk about biomass. While it's not my principal area of expertise, we will see some presentations of some specialists on that, also some videos. Then the following lectures will be about energy storage. That means how we can make fluctuating renewables, just as wind and solar, more stable. This is quite extensive, so therefore it takes 2 lectures to do that. And then at the end, I will show you some perspective and feasibility of energy transition. So we compare different opportunities in different countries and regions, especially the diesel substitution. We will have a very nice example from Princeton University about the wind park sizing, optimization, including storage and related transmission systems. We will talk about balancing power via demand-side management, for example, for controlled charging of electrical vehicles. So this is now by Mr. Bain from the year 2004, an introduction to biomass thermochemical conversion. But first, let's take a short look at the video.
Sustainable energy sources are growing in popularity, but we are here to sort the wheat from the chaff, to check out which technologies are going to make the most impact and which are likely to be less useful. I'm Afia Adam.
And I'm Ashley House. Hello and welcome to the programme. Today we're taking a look at one of the most basic of energy sources and one which energised the move from caveman to modern man: biomass and bioenergy.
Did you know that biomass-derived energy has been used since humans first discovered how to harness fire? But the biomass industry itself wasn't established until the 1970s oil crisis, when people started to look for new sources of energy.
Now these days bioenergy is about far more than just burning wood. In fact, scientists have developed highly complex methods that can transform grass into biogas and vegetable oils into biodiesel. And that new technology really is propelling organic material into a viable alternative energy source. Coming up, we visit the land of the Komodo dragons in Indonesia to see how the nation's biggest palm oil producer is improving sustainability. Waste Not Want Not, a vegetable farm in Kenya that's utilising crop byproducts to produce electricity and fertiliser. Weaning ourselves off coal, we look at the technology allowing power stations to transition to biomass. And finally, we talk to the UK's leading green energy company about plans to produce energy from the stuff under our feet, grass.
In the meantime, I travelled to the sunny Italian capital to meet our biomass expert, who's a natural resources officer at the United Nations Food and Agriculture Organization. According to the International Energy Agency, bioenergy provides 10% of world total primary energy supply, making it the single largest renewable energy source. In 2014, biofuels provided 4% of world road transport fuel and are expected to rise slowly, reaching almost 4.3% in 2020. In 2012, 370 terawatt-hours of bioenergy electricity were produced, equivalent to 1.5% of world electricity generation.
Now, when you think about the palm oil industry, you may recall headlines from the late noughties about how it's environmentally damaging.
But the industry is fighting back, responding to the criticism and changing with the time.
When you're the world's second biggest palm oil plantation company and you're feeling the pressure to be more sustainable, what do? You build a research facility. Or at least that's what Golden Agri Resources has done.
The objective of the company is to produce oil, sustainable oil, for the world demand, whatever the consumer wants to use this oil for, whether it's for food, whether it's for energy, or whether it's for cosmetic or any other purpose. But the important thing for us is to produce the oil in a sustainable way, meaning that no deforestation, no risk on the environment, and using the best practices.
Palm oil is a vegetable oil derived from the fruit of, unsurprisingly, oil palms. Most commonly, the product is used as a raw material in food production, cosmetics and detergents. But in recent years, it's grown in popularity as a source for first-generation biofuels, such as biodiesel.
That is the waste brought down to biogas by using a bioreactor, which is a completely biological process by using mesophilic bacteria to decompose the foaming and break down the waste water to generate methane gas. Methane gas being captured, purified and used at our gas engine to generate power.
Biofuels have become an attractive alternative to fossil fuels because they release fewer greenhouse gas emissions. Not only that,
When oil palm is planted,
it can continue growing for up to 30 years, meaning it has a high carbon capture value.
What is interesting with palm oil as a plant, it's accumulate carbon in the form of the trunk and in the biomass in the canopy. Every year the palm oil is able to capture about 11 tons of carbon, meaning about 44 tons of carbon dioxide per hectare per year. And this can accumulate in the biomass of the tree and be recycled every year. When we cut the fronds, we leave them decompose in the soil, enrich the soil with organic matter, means with organic carbon. And when we do the replanting after 25 years or 30 years, also all this biomass, which represent about 100 tons of biomass, let's say about 40 tons of carbon, we also recycle this in our soils.
Still, some are critical, saying that with the global population predicted to expand to more than 9 billion by 2050, growing biomass for biofuels is increasingly unrealistic. We need food and we need fuel. There's no getting around that. The solution is in developing them more sustainably.
Andrea Rossi is an expert in sustainable bioenergy and food security. He is the Natural Resources Officer at the Food and Agricultural Organization of the United Nations. Andrea, thank you so much for having us here on the gorgeous rooftop of the FAO building.
Thank you for coming.
We can see a lot of green, and that's perfect because today we're talking about biomass. So Andrea, firstly, tell me a little bit about yourself, your work on bioenergy and what exactly you do here at the FAO.
Sure, here at FAO I focus on sustainable bioenergy production and use. And in particular, I support developing countries in the design and implementation of sustainable bioenergy policies and strategies that foster both energy security and food security.
So when we talk about bioenergy, we traditionally think of developing countries where they would use, say, wood to burn to cook food. Now, just how important is that for countries like that who aren't connected to the grid?
Extremely important. Today, 2.7 billion people are still relying on traditional biomass, such as fuel wood and charcoal, for cooking. And the share of people relying on these fuels is as high as 80% in sub-Saharan Africa and 50% in developing Asia. And oftentimes these fuels, such as fuel wood and charcoal, are used in inefficient stoves and burned in open fires with no chimney or hood. And according to the World Health Organization, more than 4 million people a year die prematurely as a result of exposure to indoor air pollution linked to the use of traditional biomass.
Now, Andre, we've just heard about the importance of sustainability when it comes to using palm oil as a method of bioenergy. In your opinion, can you tell me why this is so important?
There have been concerns related to palm oil production, but there are several ways through which palm oil production can be made more efficient and more sustainable. For instance, there is a lot of room to significantly increase the productivity of oil palm cultivation, especially at smallholder level. For instance, through the introduction of higher yielding varieties and improved management practices. And if palm oil production is made more efficient and productive, then more palm oil can be produced using the same land, and there's no need for further land expansion.
Andrea, thank you so much for that. Stay with us. Now, think you know everything there is to know about biomass? Here are some common misconceptions.
You thought you knew? Think again. Myth: biomass increases greenhouse gases. Fact: Burning biomass does release carbon dioxide, but the process doesn't have to be a net emitter. You see, plants, via photosynthesis, absorb carbon dioxide. And throughout their lives, they can capture the same amount that would be produced if they were burnt. In other words, with proper management, burning biomass can be carbon neutral.
When it comes to environmental issues, you don't often hear about the inspiring nature of bovines, but actually a cow's digestive system is a highly efficient processing plant, converting biomass, mainly grass, into energy. So why not be inspired by physiology and turn it into technology?
It's taken 5 years and many sleepless nights, but finally Oxford-based eco-entrepreneur Mike Mason has achieved his vision, producing biogas from plant waste.
Anaerobic digestion is a well-established technology. Gorge Farm has hundreds of tons a week of waste, and it seemed a shame not to be using it. So I was sitting with some friends really over a beer, and they weren't aware of the technology and I wasn't aware of the scale of their waste, and we put two and two together and it became blindingly obvious that it was a good idea.
Mike's farm is close to Lake Naivasha, around 90 kilometres northwest of the Kenyan capital, Nairobi. On 700 hectares of land, they grow flowers and 20 varieties of vegetables, including baby corn, broccoli and cauliflower, mainly for export to Europe. As well as feeding people, the crops are now providing the food that fills the belly of this beast, the anaerobic digestion plant.
What essentially you are looking at is a big mechanical cow. You feed it biomass on one end, it gives you manure and liquid fertilizer on the other end, and in the process gives you biogas. Once you've got the biogas, now you've got the fuel that is required to run the next section of the plant, which is the electricity.
Anaerobic digestion is a natural process in which bacteria convert organic materials into biofertilizer and biomethane. It takes around 16 days for the conversion, with biomass working its way through these 4 different tanks.
Once we've got the biogas, we need to turn the biogas to electricity. And the way we do this is using an engine generator, gas engine generator. Essentially, this is just like an engine in a car, in a normal vehicle. The only difference is that instead of using petrol or diesel, use biogas to run it.
At maximum capacity, the biogas plant will require around 120,000 kilograms of biomass residue from the farm every day. This will generate up to 2.2 megawatt hours of electricity.
Most of the electricity goes to moving water to where it's required in the farm, and that is pumping. As for heat, what we've got is greenhouses, and greenhouses need some optimum temperature at which you get optimum production from plants. Sometimes to achieve this, the farm will use diesel boilers to heat the greenhouses. We intend to displace these diesel boilers and basically pipe the heated water to the greenhouses.
Crucially, any excess electricity that isn't required by the farm is fed into the national grid. These sorts of facilities can be replicated, supporting the environment and local economies along the way.
Recent research shows that we could speed up the process of digestion by up to perhaps 30 times. Do that and we change the whole relationship between agricultural waste and energy, and every farmer becomes an energy supplier as well as a food grower.
What are the opportunities for developing countries to develop the use of anaerobic digestion even further so more people can be connected to sustainable energy resources? And of course, what are the limitations with that?
Anaerobic digestion is a mature technology with a strong potential, and significant amounts of biogas can be produced through the anaerobic digestion of agro-industrial and livestock residues. This biogas can then be used to generate heat and electricity, and part of the heat can be used for the industrial process, and the surplus heat can be supplied to local communities through district heating systems. This type of technology has a lot of potential, but of course there are also challenges and barriers that need to be overcome. And this is again where the importance of a long-term, stable, enabling environment comes into the picture. Some of these limitations include artificially low energy prices due to fossil fuel subsidies, the high upfront investment required for the installation of the technology and its purchase, of course, and combined with high cost of capital and in some cases problems accessing credit that can be faced by investors in developing countries.
Are there opportunities for developing countries to do some sort of technological leapfrogging, skip the use of fossil fuels and move straight to renewables?
This is an issue that has been extensively debated in the literature over the past 20 years. And in my view, when it comes to modern bioenergy, a concrete example of such leapfrogging is represented by the hundreds of thousands of households that around the world, and especially in Southeast Asia, have gone from using traditional biomass, such as fuel wood and charcoal for cooking, to using biogas obtained through anaerobic digestion of agriculture and especially livestock residues for heating and cooking and for lighting. So in this case, these households have been able to move away and transition from reliance on traditional biomass to modern bioenergy technologies and services without the use of fossil fuels.
Here we see the different sources of biomass. Top left side, the forestry and crops residues, agriculture crops and residues, sewage, municipal waste, animal residues and industrial residues. These are all biomass sources. For the conversion process in the middle, we have the gasification, we have a combustion and co-firing, we have a pyrolysis, we have different types of fermentation. And as an end product on the right side, we have different fuels, for example, ethanol or renewable diesel, electricity, that's a main concern of us, heat also, but also we can make a lot of chemicals, starting with plastics, solvents, pharmaceuticals, and so on. Here on this triangle, you see the different conversion process. In principle, we deal with three different elements. Biomass consists of all of them. That is carbon, that is hydrogen, and that is oxygen. Then we have the different conversion processes. If we go more towards hydrogen, we have the hydrogasification. Or if we go towards water, it's in between hydro and oxygen. We call it steam gasification. If we oxidize it, we go more towards oxygen, and we have combustion products. In between, there are gaseous fuels. If we go more towards carbon, for example, by slow pyrolysis, we have, for example, chars or solid fuels. Or we go more towards, a bit more towards carbon hydrogen, it's coals. Here we have an overview of the biomass products and the conversion processes and the tools for them. So we have first hydrolysis. So we have acids and enzymes which provide that. As a product we have sugars and lignin. We have gasification by high heat and low oxygen. It's called syngas. We have digestion from bacteria. Then we have biogas. We have pyrolysis. That is by heat and pressure and catalysis. Then they have biocrudes. We have extraction, for example, mechanical extraction or chemical extraction. We have some carbon-rich chains. It could be a lot of products. We have separation, mechanical or chemical. Then we have plant products. These are possible end products. So we have bio-based chemicals, bio-based materials, liquid biofuels, electricity, and heat. So we have the overview of the biomass conversion process. In general, we have the fuel handling, then the conversion, then the cleaning, and finally the end use. So these are the different forms here. So we have the biomass receiving, first stage screening, storage, feed preparation, conveying, feeding. And we have the conversion process either by combustion, gasification, pyrolysis, liquefaction. Then we have the cleaning, hot gas cleaning, cold gas cleaning, tar removal. We have dust removal and removal of some unwanted residues. We have emission reduction also. Then they have the end use, heat and power, gas biofuels, liquid biofuels, or solid biofuels. Here is also a movie about biomass energy, which is a bit more profound than the first one.
Hey, welcome to our final energy source presentation, and today is looking at biomass energy. We had mentioned in class before that biomass energy was energy from recently living things, and so we're going to take a look at what does that exactly include. And so you would consider things like wood, but also trash, landfill gas, crops, and alcohol fuels. All of these things pretty much have in common the same sequence of energy transformations, and that is the energy is starting at the sun. And so when the sun comes in and it's electromagnetic radiation, it's coming down, and that energy gets absorbed by plants and is used in photosynthesis to convert that radiation energy into chemical energy. So we form up sugars, and those sugars are going to be transformed as they go through some different processes, and it's still chemical energy at that point. Ultimately, how do you get that chemical energy to become useful energy? Well, we would burn it, and so you're going to be burning your fuel, your biomass fuel, and that will produce heat or random kinetic energy, which could then use to run a power plant. When you're burning biomass, it is hydrocarbons that you're burning, and so these hydrocarbons are going to release carbon dioxide and water vapor. So at this point, you're saying, man, that sounds an awful lot like fossil fuels. And so when we look at the similarities, yes, it does have a lot of similarity in terms of where the matter is coming from. It's carbon dioxide that's been pulled out of the atmosphere and then fixed into these sugar molecules so that we're getting chemical energy. We have a lot of similarities in terms of the exhaust products that you're getting out of them as well. But a major difference is when was that carbon dioxide in the atmosphere? And when we consider biomass, it's recently living, so it recently came out of the atmosphere. When we're talking about fossil fuels, these are plants that lived a really long time ago. So this is like really old carbon dioxide that was then fixed into the chemical structure of the plants, which then got buried and became these fossil fuels that were stored underground. So that carbon has been stored out of the atmosphere for a very long time and just kind of been tucked away underground. We are taking that out in massive amounts, burning it, and putting that carbon dioxide into the atmosphere. And so the difference when you compare to a biofuel and biomass is that, well, you would be replanting new plants to grow your next crop to turn into more biomass fuel. And by doing that, you are effectively removing the carbon that was put into the atmosphere by the plants that or the biomass that you had just burned. So it's a complete cycle, and therefore it's often argued to be carbon neutral. It doesn't add additional carbon dioxide to the atmosphere because even though, yes, CO2 is coming off of the burning reaction, it is not actually new because it's been recently in the atmosphere to begin with. It came from plants that had just recently taken it out of the atmosphere. Now, other forms of our biomass energy besides like burning wood would be looking at things like landfill gas, and we've already talked about that. We've also already talked about burning trash, and that would be in this category of biomass fuels. But something that we haven't really talked about is a way that you may not even be conscious of that we use biomass energy all the time. Your car is probably running off of biomass energy a little bit at least. And what do I mean? I'm talking about this. So you go to the gas pump and you read the little sticker on there, and it says this product may contain up to 10% ethanol by volume. typical unleaded gas here in Connecticut, you're going to find about 10% ethanol, and ethanol is biomass fuel. So why are we putting it there? Well, there's a couple of things. Number one, it's been shown to reduce certain pollutants that are given off when you are combusting the fuel inside the engine. The byproducts that are given out come out a little bit cleaner when you have ethanol blended into it. And so that's one of the reasons we use that. Another argument for ethanol use is it's going to extend the lifespan of how long will our fossil fuels last. So gasoline will last that much longer if we're only using 90% of it instead of 100% of it in our gas tanks. So when we look at how do you make ethanol, what's the process, where is it coming from? We have a typical pattern for how that happens today, and that is corn. So there's a lot of corn growth in the United States, and it's not all for food. Some of that corn is for the purpose of making fuel. And if you look at crops like corn, you harvest it, you're actually using the edible part of the corn to make the fuel for a car, for example. You'd grind it up, you'd separate it into the different kinds of sugars that you have, and you distill them. Just like you're making alcohol, you're doing a distillation process, and that's basically what you're producing. And this is going to get blended into gasoline, and it burns, and it's extra fuel in a sense. So it's going to be then producing some carbon dioxide, but you would argue it's neutral because of the fact that it's getting reabsorbed by the next round of crops that you are growing that are taking that carbon dioxide in. But one of the questions that people have is this really a good strategy? I mean, after all, we're taking a food product and we're making a fuel that we can run a car on. And as this graphic shows, 8 bushels of corn could equal 21.6 gallons of fuel, or it could be enough food to feed a person for an entire year. I don't know if you want to actually eat corn for every meal of the day, but it's just making a point that that's a lot of food that we're talking about just to equal 21.6 gallons of fuel. So that's certainly a concern and something that we should think about. So some people have thought, well, wouldn't it be better if we could use the parts of the plant that aren't so useful? And so one of the ideas to take the plant matter that's not digestible, but use it in a way where we could still do the same kind of process. And this is referred to as cellulosic ethanol. And one of the ideas of a crop that we can grow really quickly and it is full of material that could be used in this process is known as switchgrass. And so we could plant this grass that grows rapidly, harvest it, and then you just have to do some extra steps. Some initial pre-treatment is necessary, and that pre-treatment usually involves shredding it up and then adding some chemicals to break things down so that you can get the regular fermentation reactions to take place. And so when you can do that, you can then produce fuel from the waste products, or what are typically considered waste products from a plant. And that seems to be an idea that's very promising. The downsides are cost. It's going to cost more. It's going to be more involved in order to do those additional steps of breaking it down in order to get the fuel made out of it. If we wanted to think about, well, are there any other issues with biomass? Well, one of the things to consider is it actually really carbon neutral? Because if in fact we're harvesting our crops with fossil fuel based equipment and we're transporting them and processing them using fossil fuel based equipment, then we're actually going to be putting more carbon emissions into the atmosphere than we're going to be taking out in the process of growing the plants and producing new biofuels. And then the final thing, you have to consider what's the impact on the soils. Year after year of growing and harvesting the same plant matter is going to deplete them of nutrients, and it's also going to get people to use more fertilizers and pesticides. So now that we've looked at biomass, I want you to consider, is this something worth pursuing? Should we be supporting biofuels for our future, or should we be looking in other directions?
See some basic definitions. What is combustion? Combustion is the thermal conversion of organic matter with an oxidant, normally oxygen, to produce primarily carbon dioxide and water. The oxidant is in a stoichiometric excess to allow complete oxidation. And we have pyrolysis. Pyrolysis is the thermal conversion or destruction of organics in absence of oxygen. In the biomass community, this commonly refers to low temperature thermal processes producing liquids as a primary product. We have the possibility of chemical and food byproducts. The gasification, the thermal conversion of organic matters at elevated temperature and reducing conditions to produce primarily permanent gases with char, water, and concentrables as minor products. Primary categories are partial oxidations and indirect heating. Potential biomass products. Biomass, syngas, we discuss a bit deeper in that, hydrogen, pyrolysis oil, whole or fractionated, hydrothermal treatment oils, biomass could be either solid in different stoichiometric compositions, so CH1 or CH4, or oxygen without oxygen, or to 6 atoms of oxygen. This is HHV, means upper heating value or a high heating value. This is in the vicinity of 16 to 70 megabtu. This is a British thermal unit. We see here, so 1 kilojoule is about 1.055 BTU, one British thermal unit. Then we have also the unit SCF, that means square cube foot. The conversion is for 1 cubic meter, it's about 35.3 cubic foots. The MEF here means moisture and ash free, because otherwise you would lose some energy to convert that moisture into steam. And then we have syngas. Major components are carbon monoxide, hydrogen, carbon dioxide. So we have the carbon monoxide to hydrogen ratio on the typical range of 0.5 to 2. The heating value, the high heating value is 450 to 500 BTU per square cube foot. We have the pyrolysis oil, so mentioned here before already. The chemical composition, the water from 20 to 30%, lignin fragments 15 to 30%, aldehydes 10 to 20%, carbonylic acids 10 to 15%, carbohydrates 5 to 10%, phenols 2 to 5%, furfuryls 2 to 5%, ketones 1 to 5%. Then we have hydrothermal treatment oils, so it's water plus alkali at the temperature of 300 to 350 degrees Celsius. The pressure is high enough to keep the water liquid, and the use of carbon monoxide is also an option here. And yield is above 95%. Distillate at 500 degrees Celsius is 40 to 50%. Distillate composition, for example, hardwood 300 degrees Celsius, then we have a CH1 or 2, or without oxygen, or deoxygen with manure at 350 degrees Celsius, CH1 or CH4, that's methane, with or with 1 oxygen atom. Qualitative, so we have long aliphatic chains, some cyclic components containing carbonyl groups, a few hydroxy groups, ethyl linkages, and carboxylic acid groups. The heating value is between 28 and 34 megabtu per ton. Let's start with combustion. The stages of combustion of solids, we have first the drying. So we take out the moisture. Then we have the devolatilization via pyrolysis or via gasification. Then we have the flaming combustion. Then we have the residual char combustion at the very end. The typical combustion reactions are, so we have carbon, this S stands for solid, so we have a carbon atom. This oxidizes via oxygen molecule. G stands for gas. Then we have as a final product a carbon dioxide, which is also gases. Or we can form hydrogen in a gaseous form with oxygen also in gaseous form to water. We have used double amount of hydrogen than oxygen to have the H2OL, and L stands for liquid. Then we have a CH4, that's methane, that's also gases, plus 2 oxygen molecules. And then we have as a product carbon dioxide, gases, and water, liquid. Here we see a life cycle for carbon dioxide and the energy balance for a direct fired biomass system. We have the avoided carbon dioxide emissions. We can put them to landfills and so on, or we can transport them, then use it in a power plant. There we create electricity, and by the combustions we relieve 1,204 grams of carbon dioxide into the air. That's about equivalent to a lignite coal plant, but altogether, because you took this amount of emissions here, you avoided these emissions, you add a negative emissions of minus 410 grams of carbon dioxide equivalents per generated kilowatt hour of electricity. Okay, we have to discuss whether this really avoided, whether this never can be released anymore to the environment. But here on this chart it looks quite promising. So here we see the effect of plant size and the costs of electricity and steam. On the x-axis you have the power plant size, and the y-axis you have the cost of the electricity, and on top you have the combustion for electricity, and the lower part if you have steam, cheaper also. Purchased electricity is still cheaper, so there's a wide gap between this environmentally friendly production to the purchased electricity. That's changing now, that's from 2004, but the biomass electricity production didn't make a lot of progress, such as wind and solar power. Here you have the sensitivity to feed costs. So on the x-axis, these are feed costs, and on the y-axis, you have the electricity costs. And it's linear, apparently. If you double the feed costs, or you have high feed costs, then you have also a high electricity costs. So we have here just a short repetition, the biomass thermochemical conversion for fuels and chemicals. So on top we have the gasification, the cleanup, and the synthesis. The products are hydrogen, alcohols, gasolines, diesel, olefins, and oxochemicals, ammonia, and synthetic fuels. For pyrolysis, we have then the conversion or collection. Then we have the purification, and also as a product we have hydrogen, oleophils, oils, and especially chemistry. The other conversions, and we have also, for example, the hydrothermal processing, liquefaction, or wet gasification. Then we have also as a final product hydrogen, methane, oils, or other ones. Here on this chart we see on the x-axis the temperatures, and on the y-axis the pressure. So up is high pressure. For example, here we have bio-oil and gas products. Here are some companies mentioned which provide that. And then at medium temperatures, 700 to 850 degrees Celsius, we feed with biomass or black liquor. You see the different products. I won't go into details. and the different companies that are able to provide that. Here we have on the x-axis the pyrolysis severity. So we have first the primary process. Now we start in solid phase, lower left part with biomass, turn into liquid phase or vapor phase. Then we have carbon monoxide, carbon dioxide, or water vapor. This is our primary process. We have primary vapors. Then we convert it further by secondary processes, which we see a short movie about it in these different products. Then we have tertiary process, which provide the mentioned products here. We'll see also a short movie about that. Gasification is nothing new. This is a picture from 1898. So this has been done there already. There's some history of gasification. So it started a long time ago. First application of artificial gas was for gas lighting in many big cities like London, Paris, Berlin. Then some processes, here also a German company, BASF, mentioned the Tropsch process. Then we have vehicles. During World War II, there was a lack of fuels, and then you were driven by wood gas. And this is a present development. The most interesting at the moment is how we can produce hydrogen. So this is an overview of the gasification pathways. So we have the biomass, then we have the preparation and handling, then we have the low pressure gasification via oxygen, and we have a shift conversion and compression, and then we take away the acid gas, then we have carbon dioxide, and as a product we have some synthetic gas. We can also do it at high pressure. Then we have the hot gas cleanup, then we have the reforming and the compression, and same as before, the acid gas removal. Then we have clean carbon dioxide and the synthesis product. Then we have at low pressure indirect gasification, then the cooled gas air cleanup, the reforming and compression. Also for the indirect gasification, then we have catalytic conditioning and reforming, again the compression, and it goes again to the acid gas removal and the synthetic gas production. These are the different reactors, the gasifiers. So we have the updraft gasifier. The biomass comes from the top. We have the pyrolysis here. The air comes from the lower part. As a result, we have the gas, tar, and water. This is the chemical reaction for it. It has some different advantages and disadvantages. These are listed here. So the advantages: mature for heat. Small scale applications can handle high moisture, no carbon in the ash. The disadvantages: they have some feed size limits, the high tar yields, scale limitations, producer gas slacking potential. And as the next, we have the downdraft gasifier. Again, the biomass comes from the top, the air comes from the lower part, and then the gas comes out from a lower part and goes up. Then the advantages is it allows small scale applications, low tar, feed size limits, scale limitations, producer gas, and it's moisture sensitive. We have the fluid bed gasifier. So we have a fluid bed. So we have the biomass from lower part and also the air from the lower gas. And we have a cyclone to remove the ash. The most important, we have the fluid bed here. This has the advantage that we can use a large-scale application. We have good feed characteristics, the direct and indirect heating. It can produce syngas. The tar removal is only medium, and we have a high particle loading. Then we have the circulating fluid bed. It's here, so it's the bed is circulating. So this has the advantage that we also have large-scale application. They have a good feed characteristics and can produce also a syngas. Same disadvantages: medium tar yield, and we have a high particle loading. And we have the entrained flow. So we have here the biomass, air and furnace, and then we have the char removal. We recycle some gas for the furnace. It can be scaled. Advantages also, you have low tar. The disadvantage is it's needed, a large amount of carrier gas is needed, high particle loading. Here's an example, the Carbona project in Skive, Denmark. So you have the feeding of the biomass here. You have the air also in lower part. You have the gasifier. You take away the gas. You use a tear cracker with a gas cooler. You take away the ash here. Again, a gas cooler. Then you have the gas tank. And you can drive a gas engine which provides electricity here and additionally heat, which can you also use.
The thermochemical conversion process uses heat to break down biomass into intermediates, such as gas or bio-oil, that can be upgraded into fuel and other products. One type of thermochemical conversion process is gasification, a method that uses heat to turn biomass into a hydrogen and carbon monoxide-rich gas called synthesis gas, or syngas. This in turn is converted into liquid transportation fuels or other products. Gasification occurs at relatively high temperatures. Here's one example of a gasification conversion process. Wood material such as forest residue is a common feedstock for the gasification process. For best results, feedstock wood chips are no more than 2 inches in size and have 20% to 30% moisture content by weight, depending on the gasifier. In the gasifier, the biomass is broken down into vapors in a carefully controlled environment that typically contains oxygen and/or steam. The syngas produced is made up of carbon monoxide and hydrogen. Char, a solid byproduct of gasification, is typically removed using a cyclone. Cyclonic separation allows removal of particulates from a gas stream without a filter by using rotational effects in combination with gravity to collect the particles. Tars and methane are also produced. Their quantity and composition depend on the gasification environment. Tars are high molecular weight organic compounds. If they are not removed, these tars will contaminate downstream equipment and inhibit fuel synthesis. One way to remove methane and tars is by using special catalysts to convert the compounds into additional syngas, thus eliminating the methane and tar problem while also improving the efficiency of the process. Additional cleaning and conditioning steps may be required to remove other contaminants such as ammonia, sulfur, and carbon dioxide. The syngas is then conditioned to produce the desired ratio of carbon monoxide and hydrogen to achieve optimal chemical reactions in subsequent steps. The pressurized hot syngas is then passed over a catalyst to form a liquid. The catalyst is contained in a reactor, and the syngas is passed through the reactor, where the carbon monoxide and hydrogen molecules combine to form larger molecules. These molecules are subsequently cooled, condensed, and refined into clean, renewable transportation fuels and other products. The Department of Energy has supported development of innovative technologies that result in higher yields and superior quality of biomass syngas. These efforts have also resulted in a much more thorough understanding of the gasification process. Enabled by these advancements, industry is deploying gasification technologies that will bring clean, renewable transportation fuels and other biomass-based products to the marketplace.
Here you see the contribution to hydrogen price. So we have a low pressure indirectly heated gasifier system. It's designed for 2,000 tons a day, and we have costs of $30 per ton of dry feedstock. So this is the main cost drivers, 41%. They have some costs for feed handling and drying. We have costs for gasification. We have costs for the compressor. We have costs for reforming, heat exchange, and so on. And the steam, it's a negative price because we can sell that steam. Here again, a life cycle of greenhouse gases for a biomass power system. you see that we take a lot of carbon dioxide from the environment and release some of it. You need additional energy for transportation and processing and power plant operation. In total, you end up at 49 grams of carbon dioxide per kilowatt hour. That is quite good. Compare it to gas or methane, which is in the vicinity of 500 grams of carbon dioxide per kilowatt hour of electricity, or to coal, which is in the vicinity of 1,000 up to 1,150 grams of carbon dioxide per produced kilowatt hour of electricity. You can also make fuels for driving from biomass, for example, ethanol. So you have the biomass, the feed preparation, the gasification, the climate and conditioning. Then you have the syngas. Then you do the bioconversion, separation, and finally you have the ethanol. We come to pyrolysis. So what is pyrolysis? Pyrolysis is a thermal decomposition occurring in the absence of oxygen. It's always the first step in combustion and gasification processes. It's known as a technology for producing charcoal and chemicals for thousands of years. See a short movie about this.
A visualization of the biomass pyrolysis process. Biomass storage and drying. Wooden or agricultural biomass stored in a dedicated storage facility is transported to the pyrolysis reactor via a bucket feeder. The raw biomass is pre-dried inside the feeder through the use of hot and dry air flowing in the crossflow. Biomass pre-drying has a positive impact on the reduction of the moisture content inside the process material by a few %, and additionally increases the pace of the processes occurring in the following stages. Biochar production. Pre-dried and preheated biomass then goes to the pyrolysis reactor, where the following 4 processes take place. The moisture evaporation process. All the moisture accumulated in the raw biomass has to evaporate in order to initiate the carbonization process. Depending on the type of biomass and the amount of moisture accumulated in the process material, it can take from several to more than a dozen seconds, and its efficiency is due to the high temperature in the upper part of the reactor. The degasification process. In the next stage, the biomass is degasified in the temperature range of 370 to 400 degrees centigrade, within which range the removal of volatile particles is most efficient. Chemical compounds like nitrogen, carbon monoxide, carbon dioxide, hydrogen, and others are flammable, and approximately 40% of the energy yield is consumed by the pyrolysis process. After mixing with the humid air from the preceding process, the remainder of those gases can be used for energy. The carbonization process. Dried and degasified biomass is treated with high temperature. This process results in the quick concentration of elemental carbon and the disappearance of the fibrous structure, improving its grindability. Depending on temperatures inside the reactor and the duration of the carbonization process, the ready material can have a calorific value in the range of 21 to 29 megajoules per kilogram. The cooling process. The ready material is cooled to ambient temperature with the use of the cross-flow water cooler. In the next stage, carbonized biomass is loaded to big bags, pelletized, or transferred directly to the boiler. Heat generation. The flammable gas has a relatively low calorific value, so the best way to make use of it is by conversion to hot water. Pyrolysis systems with productivity from 300 to 1,000 kilograms per hour can supply district heating networks with a maximum capacity from 1 to 3 megawatts respectively. The yield of flammable gases depends on the type and quality of the processed biomass and the expected characteristics of the carbonized biomass. In order to maximize the efficiency of the pyrolysis process, hot air taken from the coat of the reactor is used in the biomass pre-drying process. Hot air is transferred to the bucket feeder, which was illustrated some time ago. At the end of the process, all gases are mixed and emitted through the common stack.
From the products of biomass pyrolysis is if we use fast pyrolysis, we have 75% of liquids products at moderate temperature and short residence time, 12% of char products, and 13% of gaseous products. If we use carbonization, we have only 30% of liquid products at low temperatures and it's long residence time. And as the name suggests, we have a lot of solid products, char with 35% and 35% of gaseous products. Then we have the gasification. It occurs at high temperature and also at long residence time. We have 5% of liquid products, 10% of solid char products, and 85% of gaseous products. Let's take a look at the fast pyrolysis process. So fast pyrolysis is a thermal process that rapidly heats biomass to a careful controlled temperature in the vicinity of 500 degrees Celsius, then very quickly cools the volatile products within 2 seconds or less, which have been formed in the reactor. It offers a unique advantage for producing a liquid that can be stored and transported. Has been developed in many configurations. At present, it's still at a relatively early stage of development. The requirement, so first you do the drying. You have to get less than 10% of moisture. Can use the feed and reaction water in bio-oil. Then the comminution in 2 mm bubbling bed or 6 mm of circulating fluid bed. Then we have the fast pyrolysis. This is at a high heat rate, controlled temperature, short residence time. Then we have the char separation, and then we have the liquid recovery, for example, by condensation or coalescing. Some typical operation pyrolysis units from different companies. So we have from Dynamotive about 400 kg per hour or 20 kg per hour by RTI. There are many research units. At the circulating fluid beds, we have some examples here between 1000 kg per hour and 20 kg per hour. The rotating cone, some examples in the Netherlands with 200 kg per hour. Vacuum, we have 3500 kg per hour at Pyrovac. We have the Auger pyrolysis at 200 kg per hour at ROI. So this is a bubbling fluid bed pyrolysis. So we have the fluid bed reactor, and then we have the bio-oil, and as a main product, the gas, either fluid form or exported in a pipeline. Here you see such an example from the UK, a plant which digests 250 kg per hour in Wellman. The advantages of fluid bed reactors are they have a good temperature control. The char removal is usually by ejection and entrainment, separation by cyclone. It's an easy scaling, well understood technology since first experiments at the University of Waterloo since the 1980s. The disadvantages are that a small particle size are needed. The heat transfer to a bed at large-scale units have to be proven still. Come to the circulating fluid beds, CFB. We have a circulating fluid bed. You see here the hot sand, which is used there. We have some flue gas, and here again the gas production as a byproduct, the bio-oil. The advantages also they have a good temperature control in the reactor. A large particle size are possible. They are suitable for very large throughputs. It's a well understood technology. Disadvantages are the hydrodynamics are more complex and we have larger gas flows in the system. The char is finer due to more attrition at higher velocities, so we have to separate it by a cyclone. Closely integrated char combustion requires careful control. Also, the heat transfer to bed at large-scale systems had to be proven. Here you see a rotating cone, BTG. Centrifugation drives hot sand and biomass up a rotating heated cone, here in red color. The vapors are condensed, the char is burned, and the hot sand is recirculated. You see how the particles are lifted up here. Vacuum moving bed. It was developed in Canada, scaled up by the company Pyrovac. We have pilot plants operating at up to 50 kilograms per hour. Demonstration units are at 3.5 tons per hour. Analogous to fast pyrolysis, as vapor residence time is similar. We have a lower biofuel oil in the vicinity of 35 to 50%. It's quite complicated mechanically, stirring wood bed to improve the heat transfer. The Auger reactor, developed for biomass pyrolysis by the company C-Sweep, then by ROI. It allows for 5 tons per day or 200 kilograms per hour. A mobile plant. It was designed to be moved to chicken farms and then can make pyrolysis of chicken litters on site. It's compact and it does not require a carrier gas. Relatively low process temperature at 400 degrees Celsius. We have lower yields in bio-oils. We have moving parts in the hot zone. We have still the problem with the heat transfer at large scale. Char removal. Char acts as a vapor cracking catalyst, so rapid and effective removal is essential. Cyclones are usual method for char removal. Fines pass through and collect in a liquid product. Hot vapor filtration gives a high quality product free of char. Char accumulation cracks vapors and reduces liquid yields by about 20%. Limited experience is available. Liquid filtration is very difficult due to nature of char and pyrolytic lignin. Liquid collection. So primary pyrolysis products are vapors and aerosols for decomposition of cellulose, hemicellulose and lignin. Liquid collection requires cooling and agglomeration of coalescents and aerosols. Simple heat exchange can cause preferential depositions of heavier fractions leading to blockage. Quenching in product, liquid and immiscible hydrocarbon followed by electrostatic precipitation is preferred method. Bio-oil is water miscibles and is comprised of many oxygenated organic chemicals. The properties are the following. It's a dark mobile liquid. It's combustible. It's non-miscible with hydrocarbons. The heating value is about 17 megajoules per kilogram. Its density is 1.2 kilograms per liter. It's acid. This pH value is 2.5. It has an odor. It ages. That means that the viscosity increases with time. Upgrading of bio-oils. So there are physical methods. So filtration for char removal, emulsification with hydrocarbons, a solvent addition. Chemical methods. So we have reaction with alcohols, catalytic deoxygenation. So we have the hydrotreating, catalytic or cellulite vapor cracking. Here we have some applications of bio-oils. So we have the extraction process, which can then be used directly for chemicals, or we have an upgrade process. Then it can be used in a generator to produce electricity, or we can use it as a fuel for driving vehicles. We can use the extract for heat and also generate electricity by a steam engine or so. Bio-oil costs. So these are by these two companies. They say, okay, it's $4 to $5 per gigajoule of heat. Base costs are $68 to $75 per ton. BTG says it's $6 per gigajoule of thermal energy. Costs are in the vicinity of $100 per ton. Just as a rough estimation by this formula. So if the cost in US dollar per gigajoule is the wood costs, so it's in US dollar per dry ton, divide by 10 plus 8.87 times the wood throughput to a power of minus 0.347 dry tons per hour. Why is bio-oil not used more? The costs are 10 to 100% more costly than fossil fuel. The availability, there are limited supplies. The lack of standard and inconsistent quality inhibits wider usage. Incompatibility with conventional fuels, unfamiliarity for users, a dedicated fuel handling is needed, and it has a pure image. The end will show some research opportunities on these fields. So these are the technical barrier areas. Still some research is needed for the feed processing and handling, for the gasification, conversion, gas cleanup and catalytic conditioning, the syngas utilization, the process integration, and the process control, sensors and optimization, all with the idea to lower the relatively high costs. Here are also some suggestions for the research of what could be done. Further on, there are other options for biomass use. The advantage is it's quite controllable, so we can provide flexible power, which is in complementarity to wind and solar power. You can use also biomass to bind carbon dioxide. You can use growing biomass in trees and grass to cool by evaporation. For example, in big cities, this is quite noticeable. If you have a lot of trees in the cities, then the temperature is significantly reduced. And by that, you save energy for air conditioners and so on. These are some possible readings suggested by Mr. Bain. And next time we will talk about storage for 2 lectures. Thank you very much.